Good morning, student. Today we will discuss Bernoulli principle, which states that the sum of pressure energy, kinetic energy, and the potential energy of unit volume is constant. P stands for the pressure energy. Half rho V square, it is the kinetic energy per unit volume, and rho stands for rho GH stands for the potential energy. And this is the sum of all three energies is constant in a tube in which a liquid is flowing, and that liquid of non-viscous liquid, incompressible liquid. So this is our tube having different area of cross section. Here we have area of cross section A1, and here we have area of cross section A2. The liquid is moving in, so its velocity is V2 here and V1 here. So what will be the work done? Work done to move liquid inside. Here the liquid is moving in, so that work done will be work done to move in W1 force into displacement. Now here we have the liquid is moving up to this distance, and that distance is d. We can change that distance for very short interval of time. Work done to move in distance is equal to V1 into delta t. This distance, because liquid is flowing, so velocity equal to distance upon time. So delta t. So work done will be force F1 dot V1 into delta t. Equation 1. But that F1 also we can write. What we can write for F1? We can use the definition of pressure. It is equal to force upon area. So this force F1 will be replaced with P into A. So W1 it is equal to P1 A1 V1 into del T. This is our work done on water. What we can say? The work done on fluid. And this work done due to the external edges. Now when fluid is moving out, here the fluid is moving out, so work done by fluid now. W2 is the work done at second other end, and it will be W2 which is equal to the work done at other end will be P2 A2 V2 into del T. So the total work done or net work done will be W2 minus W1 or W1 minus W2. The net work done will be W1 minus W2. We can provide equation number. Here equation number 1. This is equation number 2. Now where this work done will appear? See, this cross-sectional area, it is at height h1, and this cross-sectional area, it is at height h2. So the work done will appear in the form of change in kinetic energy as well as change in potential energy. Because it is moving here, so first of all we will see the change in kinetic energy. Change in kinetic energy. Velocity is v2. Velocity of moving liquid is v1. So change in kinetic energy 1 upon 2 m v2 square minus 1 upon 2 m v1 square. Apart from this, the net work done will appear in the form of increase in potential energy. Here height is h1 and here height becomes h2. So the work done will appear in the form of increase in energy also. Which energy? Kinetic, potential energy. So change in potential energy, it will be mgh2 minus mgh1. This will be the equation 4. So according to conservation of energy, the work done will appear in the form of change in kinetic energy plus potential energy. So now we can, here its position is h1, its position is h2. So work done will be equal to work done W1 minus W2. This is equal to change in Ke plus change in P. P stands for change in PE. PE stands for potential energy. So put the value of all these equation 1 to 3 here. We will get, this is net work done, W1 minus W2. W1 minus W2, this is equal to 1 upon 2 M1 or M, we can write M1 V1 square, M2 V2 square, M V2 square minus M V1 square plus mgh2 minus mgh1. Put the value of W1 and W2. W1 is P1 A1 V1 del T minus P2 A2 V2 del T. This is equal to half mv2 square minus half mv1 square plus mgh2 minus mgh1. Now here A1 V1 from equation of continuity, A1 V1 it is equal to A2 V2 and both will be same. So we can write A1 V1, AV we can write A into V. So P1 AV del T minus P2 AV into del T. Again AV del T is common. AV del T is common. So it will be P1 minus P2 What will be the dimension of V into dt? So V into dt, it will be distance. So area into distance P1 minus P2. This area into distance, it will become volume. So volume P1 minus P2. At the same time, we can go with the right hand side also. Take 1 by 2. M is common from this side. Here 1 by 2 M is common. V2 is square minus V1 is square. Here M and G is common. We can write H2 minus H1. Then 1 by 2 M V2 is square minus V1 is square. Total M is common. Put 2 here plus you can write G into H2 minus H1. So here the same step. Then this V will come here. So when we write here P1 minus P2, this will go here. M by V, V2 is square minus V1 is square upon 2 plus G upon G H2 minus H1. What will be mass upon volume? It will become density. So P1 minus P2, it is equal to rho V2 square minus V1 square by 2 plus rho G H2 minus H1. Why? Because we have multiplied. Here we can write rho. So when you multiply with rho, this will become rho V2 minus V1 and rho G H2 minus H1. Then P1 minus P2, rho V2 square by 2 minus rho V1 square by 2 plus rho G H2 minus rho G H1. Then 2 bring at one side and 1 will be at one side. So P1 plus half, this will come this way, rho V1 square plus rho GH1, and this will go that side. So P2 plus half rho V2 square plus rho GH2. The sum of three energies, pressure energy, kinetic energy and potential energy at this end must be equal to the sum of three energy, potential energy, kinetic energy at this end. Hence, it will remain constant for all, means for all the times, and that is what we have in Bernoulli case. Thank you.